The last two reactions for phase one start here with reaction 4, aldolase. So what's happening here is we're going to have fructose bisphosphate aldolase, which will go ahead and cleave our fructose 1,6 bisphosphate into two different products, dihydroxyacetone phosphate and glyceraldehyde 3 phosphate. So what it's going to do is cleave between the C3 and the C4 carbons, giving you two triose phosphates. So notice that this is going to give us then something symmetrical. So we're going to go from 6 to 3. So it's actually going to cut this about in half. So the reaction, when you look at the standard delta G value, you see this relatively high endergonic reaction. But thanks to the actual physiological concentrations of the reactants, this actually is actually a lot closer to equilibrium than you would expect. So again, we see that the concentrations of our reactants and products play a really heavy role in what allows these reactions to move in a forward direction. This is essentially the reverse of an aldol condensation. So back from your organic chemistry days, you guys studied your aldol condensations, and this is just going backwards. So all you really have here is, that was back when we've taken some sort of something with a double bond, making an attack on your carbonyl carbon. But this is, instead of condensation, this is then cleaving those things. So there's going to be two classes and two different reaction mechanisms that go with these. So in class 1, what you have is you're going to have a lysine residue on your enzyme play a really important role in forming a Schiff base to that substrate. So here we actually have a covalent mechanism. So there is actually a covalent bond formed between the enzyme and the substrate itself. As that Schiff base is then formed, another residue can then do some acid-base chemistry to complete the cleavage reaction. From here then, we are going to, of course, have the mechanism completed because we need to then break that covalent bond so that our Schiff base will then be hydrolyzed so that we can get our final product released. The class 2 mechanisms is going to have a completely different set. So in class 2, which are present in bacteria, class 1 are present in mammals and plants. So class 2 in bacteria, this is actually going to use zinc. So this is going to be a metal catalysis. So you're going to require a metal in order to make this work. So you've got an active site zinc, which is going to stabilize the enolate intermediate. And so there's absolutely no covalent modification. There's absolutely no covalent bond between the enzyme and the substrate here. So the zinc is enough to stabilize everything. Moving on to the last reaction in phase 1. This is where what we're doing is that dihydroxyacetone phosphate is all well and good, but in order to continue in the pathway, we really just want that glyceraldehyde 3 phosphate. So what we'd really like is we'd like 2 molecules of glyceraldehyde 3 phosphate. So there is a triose phosphate isomerase to make that reaction complete. So what this is going to do is it's going to let both halves of that aldose cleavage go ahead and continue on in the glycolytic pathway. This is going to have an enediol mechanism, and it's also going to have a glutamic acid residue serving as a general base, which is kind of interesting. This enzyme itself is actually near perfect, so when we look at that Kcat over Km, you're going to see a really beautiful approach to the diffusion controlled rate that's associated with it. Here's our structure again, where you can see the substrate in cyan there in the middle, kind of surrounded by a variety of beta sheets and then surrounded by your alpha helices. As far as our mechanism goes, as we go about this, what I want you to realize is that we're going to see a lot of things that are fairly similar to when we were looking at our other isomerase earlier. We were looking at the phosphoglucoisomerase enzyme. So before, we were going from glucose to fructose, and we were glucose 6-phosphate to fructose 6-phosphate. And there we were looking at going from an aldehyde to a ketone. Here, as we start with dihydroxyacetone phosphate and moving to glyceraldehyde 3-phosphate, we're actually starting with a ketone and we're moving to an aldehyde. But you actually see a very similar chemistry as we go about this. Just a reminder, since we are using a glutamic acid residue, here in the diagram you notice that that is glue 165. That's because we're looking at the mechanism specific for yeast. And so in yeast, it's the 165th residue. But again, we're going to use that glutamic acid residue to abstract a proton off of dihydroxyacetone phosphate, which then will lead us to an enediol intermediate. I've got that lovely double bond between the two carbons. And then finally, what will happen is you'll get a proton added across that double bond to then move that ketone to the aldehyde at the end. And that is going to leave us with 2 molecules of glyceraldehyde 3-phosphate, which will start us off at the very top of phase 2.